Okay, good afternoon, everyone. My name is Tong Yuan. I'm from Zhejiang University. The title of my paper is 0.45 degree per hour Lissajous Frequency-Modulated MEMS Gyroscope. I will introduce my paper from these parts. The first part is research background. MEMS gyroscopes have developed a variety of operating modes over the decades, and the traditional amplitude modulated mode gyros have reached the navigation grade performance in terms of angle random walk and the bias instability. But its high temperature dependent errors hinder its improvement. So in order to enhance their performance, the temperature compensation measures must be taken. And common temperature compensation techniques such as improved interface circuit, the gyro structure optimization, or software algorithm compensation. But this compensation techniques will enhance the complexity of the gyro systems. Compared with M gyroscopes, the frequency-modulated gyroscopes have better intrinsic temperature performance, so it attracts much attention. But it still have a big gap in noise and bias instability. Okay, let's introduce the background of FM gyroscope. In 2006, the concept of FM gyroscope is proposed by Hans Moser. However, the free vibration mode has poor stability, and the mode matching FM gyros has locking effect at a low angular velocity. So later, the University of California, Irvine proposed a frequency differential operation, and later the UC Berkeley proposed a counter frequency modulated gyro. It results the angular velocity by the frequency change of the vibrating mass operating the clockwise or counterclockwise. But the resonant frequency of the gyro will fluctuate with the temperature. So they posed a dual digital mask to suppress the fluctuations influence. But the two identical masks pose a greater challenge to the process. So later they proposed the indexed frequency modulated gyros. It periodically flips the two modes by a square wave so that the two modes can alternate with a phase difference of 90 degree and the counter minus 90 degree. Each mode eliminates the impact of resonant frequency fluctuations with temperature, but the high rating flips deteriorates the noise performance. Subsequently, they proposed the Lissajous frequency-modulated, and this mode is suitable for the mode mismatched FM gyroscope, and the angular rate is modulated by the frequency difference of the gyro, so it is attract much attention. Apart from the UC University of California, there are some others research student institutions to report the FM gyroscope results, such as the University of Tokyo, Japan, proposed the FM gyroscope with a clockwise and the counterclockwise mode separator, and the Polytechnical di Milan proposed the ASIC integrated FM gyroscope test results. It's great, and the Zhejiang University, that is our team, proposed a dual digital phase-locked loop structure and reported the first bias instability below 1 degree per hour. So this table is a comparison of some reported FM gyroscope, and we can see that although the temperature sensitivity of the FM gyroscope is better than M gyroscope, but it's still a challenge to stabilize the variability below 1 degree per hour, and the angle random walk is worse than by M gyroscope due to the frequency digital circuit noise. And in response to resolve the problems, we proposed a dual digital phase locked loop structure for the FM gyroscope. And we first suppressing the influence of driving force misalignment angles to further improve its performance. Okay, let's introduce the basic principle of LFM gyroscopes. In their work, the two working modes are excited to vibrate at their respective resonant frequencies, and the angular random walk is demodulated by the different phase difference of the two modes. So we can get the angular random walk. We can get the angular information by the demodulation by the frequency sum of two modes, and when we control the rate in amplitude is to be the same, and the damping coefficients influence in the zero bias is suppressed, and which realize the better temperature characteristics. And this is a typical principle of FM gyroscope. And when we consider the driving force misalignment angles, and we can see that the angles will cause a certain zero bias error, and it wasn't the bias instability of the FM gyros. So we will suppress its influence later. This is this is a diagram of our FM gyroscope, and we can see that in our structures, the two modes are experiment to face the locked loop on the FPGA, and so we can track the resonant frequencies with direct frequency readout instead of the specific frequency digit circuit chips. So we don't have the background noise of a specific FDC chip. And to suppress the influence of driving force misalignment angles, we will use parametric excitation method. According to the deduced before, we can see that the driving force misalignment angles influence the zero bias instability by equivalent damping coefficients. So in maintaining constant equivalent damping coefficients, we can stabilize the misalignment related error term in the gyroscope's bias. And the equivalent damping coefficients is the ratio of the amplitude of driving force and the rate, so we can keep them stable. So we use the parametric excitation method. And in this structure, we all keep the amplitude of driving force is constant, and we will make the rate amplitude is stabilized by adjusting the signal, pump signal of the parametric excitation module. And this is the experiment platform of our gyroscopes, and we use a multi-ring gyroscopes with a spider wave-like structure. And the right figures is our basic parameters test results, and the resonant frequencies of our gyros are about 4,450 Hertz, and the quality factors of our gyros are nearly 200,000. And this is the temperature test results, and the left figure is the zero bias temperature results, and the right is the scale factor temperature results. And we can see that the total zero bias and the total scale factor is good at suppressing the single drift, and we can realize the better temperature characteristics. But the scale factor's temperature stability has a certain temperature characteristics. Its test results is 48 ppm per degree Celsius. It's not a very good results, because there are some chips such as ADC and the DAC, and these chips will have intrinsic temperature characteristics, and so it worsens our temperature performance. And we also tested the scale factor non-linearly, and the left is, and in the range of minus 50 degree per second to 50 degree per second, the result is 166 ppm. And right is our Allen deviation test results. And before and after misalignment angles separation, the bias instability improves from 0.6 per hour to 0.45 degree per hour, and our angle random walk is 0.414 degree per root hour. Okay, compared with our work results and with other FM gyroscopes, we can see that although we don't have a good test results in temperature sensitivity of scale factor, but we have still a big breakthrough in the bias instability and the angle random walk. And in the future, we'll improve our temperature sensitivity, and we'll still study it in the future. Okay, thank you for your attention.